Hi, I'm Ansley.
And I'm John.
And we built a 3D microscope for...
All things are 3D in.
A 3D printed microscope for our project. And it came in a few different pieces. We assembled this. And then it also came with these, which hold the lenses. At this end, we have two that form the eyepiece, and at this end, we have two lenses that form the objective lens. And it fits together like this. Super fun. We've glued the lenses into here so that they don't move and so that they're centered towards each other.
If you're doing this at home and you're gluing in lenses, be very, 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 very careful not to get any super glue on the actual outside of the lens. It will not come off.
Yeah, it messes it up real bad. We learned that the hard way. But once we did that, it was cool. Like, we got them in there. They're working. It's pretty neat. Then they go in here, which...
The optical tube.
This is the optical tube. It's got gears on it so we can adjust the microscope to where it needs to be. Then it goes this hole here.
Nope.
Yes, it does. Oh, the other thing, to be able to test what we're testing, we're putting it in upside down. This is because instead of looking at it from the bottom like you usually would, we're shining the laser light in from the top and measuring from down here.
Tell the kids back home what we're testing, Ansley.
We're testing the magnification equation. That means that, like a microscope does, it magnifies things, and the equation that it magnifies according to is negative L, which is the length of the optical tube, times 25, which is the half plane distance. What is that called? The eye distance.
The near
point
distance.
There it is.
How close your eye can focus an object.
Right. So minus L times 25 over the focal length of the objective lens times the focal length of the eyepiece. And inside these, when we showed you the lenses, those are all Kodak lenses, which have focal length of 35 millimeters. So we have 4 of those in there, and we figured out the focal lengths of our effective objective lens and our eyepiece. And so we're able to theoretically calculate the magnification. And so what we're doing now is we're empirically testing that. And so what we do is we have our setup with now our objective lens at the top and our eyepiece at the bottom. We have set the eyepiece so that the focal length is a distance away, and we take our laser light, which we have built out of a...
just an LED, just a diode, a red diode.
A red diode. We stick it up here into the pinhole for the light, and out the bottom, I don't know if we can show you this without blinding everybody, but out the bottom comes red laser light. Yay!
We had a screen.
For light. And so what we've done is we have measured the beam width of the laser, and we've measured beam widths of the magnified beam at the bottom. And in order to get more than one set of data, we set it, take a set of data, reset it, take a new set of data, and from that we were able to get statistical errors and compare using standard deviation and percent error. And that is our microscope. So, yay.